As promised, we're talking about projectile motion today.
Car sacrificed.
What's that?
Car sacrificed.
A car being sacrificed, yeah. Things dropped and cars sacrificed. But first we got to talk about what's going on with how things move across the page. Oh, there it is. Got a car right here. And I know that when a car drives on a road, here's the profile view. As it drives across the road, I know that we talk mostly about the x velocity. True? Now, if you take a car and you drive it off of a cliff, it's obviously going to have an x velocity, but it's also going to have a y velocity. And once upon a time, we looked at a basketball that was being thrown, right? So we have some of that sort of in our background knowledge. But what we say with projectile motion is that, for our purposes, we will assume that motion in the horizontal direction is uniform for projectile motion. What we mean by that is it has a constant velocity. Constant velocity in the x direction. So this horizontal motion has that constant velocity. And as I look at this, it's a stroboscopic image. This is actually a tennis ball where one tennis ball was dropped down, and you can see there are some horizontal lines in there showing that it changes its rate of descent. Yeah? Yeah, sure, absolutely. Guys at the back, if you want to put the blinds down, you're welcome to. If you're cooking at the back, you're allowed to do that anytime.
Just so that there's no glare.
Oh, you just can't see because of the glare. Okay, yeah.
And you're there.
Awesome. Okay. So then, with this guy here, it's actually a little bit harder to see because of the black background. But if you take a ruler, you can take a ruler if you want to. What you notice is that this ball travels the same horizontal distance with each unit of time, because each of these images was taken at an equal interval of time. And so horizontally, the ball that's following the parabolic shape actually is moving horizontally at the same displacement per rate of time. The one that's falling vertically increases its rate of displacement as it falls. You can kind of see that with the lines in the background, right? Anyway, the way we express that is that it has a constant velocity in the x direction. Now in the vertical direction, like we can see over here on the right-hand side, the vertical component of motion will be influenced by gravity. We'll put that in writing. The vertical component of motion is influenced by gravity. And it doesn't surprise anybody that if I take a baseball and I drop it, then its motion is going to be influenced by gravity. It's going to fall down, it's going to pick up speed, it's going to travel more distance in a uniform amount of time, it's going to be influenced by gravity. But if I roll the baseball across the tabletop and I just let it go, roll, you know that the gravity doesn't operate in the horizontal. We all know that the gravity doesn't operate in the horizontal, right? Like if I let this thing just roll across a tabletop, if it was a frictionless tabletop and drag wasn't a thing, wouldn't the baseball just keep on going forever? That tells us that gravity's not working on it. And if drag wasn't a thing, like if I was on the moon and I dropped a baseball, of course it will fall in the vertical because gravity operates on it in the vertical. So those are some basic truths that we kind of know. Baseball's a nice way to talk about it. It could be any ball. But the statement that we would say is that Vy will change due to what we're going to call acceleration due to gravity. Now I'm going to write it as A subscript g. If I really wanted to press it, it is a vector. And around these parts, we're going to claim that the value of Ag is 9.81 meters per second squared. And this will have already shown up in your homework. And we'll say that it's operating down. Okay? So you can make use of that on evaluations. Now there'll be other people that online, if you're looking at some online tutors or something, they may say 9.79. And the reality of it is, and we'll talk more about this in the next unit, that value actually isn't uniform over the surface of the Earth. It turns out the gravitational field intensity at the surface of the Earth is not constant. And that has to do with a couple of factors. One of them is the fact that the density of different parts of the Earth isn't the same. The other thing, though, is, and the more major issue, is that the Earth isn't a perfect sphere. It's sort of what we call an oblate spheroid. So that means that whether you're at the equator or the North Pole, you're actually at a different distance from the center of our planet. So that 9.81 is not a constant around the surface, okay? So if you see different values online or in different textbooks or whatever, you say, oh, okay, well, it was probably published by somebody that lives somewhere else. And we're okay with that, okay? So in this room, right now, we're going to say 9.81 though, okay, for our evaluations. Anyway, now think about this person and their cliff. And it looks like there's a car and there's a person, and I want to say that the person is going to drop an object, like we can just say that it's a ball, off of a cliff. But before we do that, we need to have a reference frame. So we're going to have up, down.
Front, back.
You know what, I'm going to say right, left. I'm going to make, just for argument's sake, I'm going to make down be positive and up be negative. I'll make right be positive and left be negative. And it seems to me that if I drop a ball, oh look, there's already dots on the page. I'll just make them darker. Seems to me that if I drop a ball, the ball's going to get faster, 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 just like in that little stroboscopic image in the top right-hand corner. By the way a stroboscopic image gets generated is that they drop balls, for example, and they just leave the shutter open on the camera. So whether it's film or a CCD camera, an electronic camera, they leave the shutter open and they literally flash a strobe light at equal time intervals. And by flashing a strobe light at different equal time intervals, you actually get that multiple exposure. Now, if you're somebody that doesn't want to use like the old-fashioned strobe light, you can actually use a camera that does multiple exposures simultaneously, in sequence, and then you can overlay the layers. And that's more of a Photoshop way of dealing with it. But the traditional way was to just leave the shutter open and let a strobe light flash at it multiple times. So if you're playing around with this kind of thing, if you're in photography class, you could probably make kind of a cool effect with this if you have a flash, like a flashing light. I have some strobe lights in the class. If you were in photography and you wanted to borrow one for an effect, you definitely just talk to me. If you're responsible, I'll say yes, okay? So here we're dropping this ball, and we're just saying it's like a ticker tape, and as it falls, I know it's going to start from rest because the language that we use when we talk about dropping things is that things start from rest. It's going to pick up speed. So that by the time it hits the ground, it's going to be going quite fast. And I could even make statements like the velocity 1 in the y direction for the ball is 0 meters per second. But you know, I could also make a statement about this ball that velocity 1 in the x direction is 0 meters per second. Which almost seems like a no-brainer, but yeah, if I dropped it, it's not going in the x direction, right? But then when it hits the ground, I can say, oh, okay, well, I watched this thing, I got a speed radar, and I say, hey, v2y, when it hits the ground, is 40 meters per second. I can even say 40.0 meters per second when it hits the ground. 40.0 meters per second. That says 40.0 meters per second. Okay? We got a little bit of messiness. Let's clean it up. Okay, 40.0 meters per second when it hits the ground. But then when I say v2x, is there anybody willing to be brave enough to say this? What's the x velocity when it hits the ground? Yeah? 0. Still 0. It's moving fast, but not in the x direction. Right? That's the story I'm telling. Now, the car. Now, this car is driven by a stunt driver, okay? So I'm going to be really careful about how I draw the picture. Stunt driver drives the car towards the cliff, bails out at the last second. Nobody's damaged or hurt in the filming of this video or whatever, you know? But this, don't draw it until I'm done, because I want to make sure that everybody is doing the same thing. And it's really, really specific. The car gets to here. And then the car gets to here. And then the car gets to here. And as this car goes, somebody's going to look at this and say, well, that's not quite a straight line. That's a parabola. We see this downward-facing parabola. It's like, oh, yeah, definitely. It's a downward-facing parabola. But another thing that I might notice, and things that we can use as sort of like touchstone reminders from previous conversations, is that if I drew a dotted line down, and a dotted line here, I think that we can recognize that if I extend these dotted lines all the way up to the top of the page even, that this distance, and this distance would be uniform distances. Just like my stroboscopic picture of the tennis ball previously, right? You're coasting along, if you like, in the x direction at a constant velocity. There ain't no gravity. There's no gravity in the horizontal direction. You know, can you imagine if there's gravity in the horizontal direction? You'd have somebody that like jumps up in the air, like, woohoo, I'm jumping up in the air. Here's the ground. And if gravity operated in the horizontal direction, wouldn't they jump up and expect to zoom sideways? That doesn't make sense. It's ridiculous. If anybody does a jumping jack and they slide sideways through the air, something funny is happening, right? You don't accelerate sideways. Gravity only operates in the vertical. And everybody kind of just expects that. We've all lived with it. It's normal. So when I look at this and I see that it travels horizontally at a constant velocity, it doesn't shock me. I'm totally cool with that, right? And I have to have like an understanding of why. It's because gravity doesn't operate in the horizontal. Now, people that are like super detail oriented, they'll say, wait a minute, shouldn't it slow down in the horizontal? Why would it slow down in the horizontal?
Air resistance?
Drag, yeah. The truth of the matter is, it actually would slow down in the horizontal. What we're going to do, this is one of our assumptions that we're going to interpret our problems through the lens of. We're going to simplify this. We're going to say we're going to assume no drag. Okay? So assuming no drag, it would move forward at a constant velocity. But if you're a real detail-oriented person, you might say like, oh, I know that a golf ball experiences drag. I mean, that's a whole reason why you slice or whatever it is somehow the air is impacting the movement of the ball. It's also why your golf ball doesn't go on, you know, quite as far as you would like it to, because there's drag acting on the golf ball. That's just true. Anyway, if I take a look at this and I say, hey, wait a minute, I'm going to think about y components. For this car, it would have a y component at this moment of time that looks like this. It would have a y component that looks like this. It would have a y component of motion that looks like this. And if you reflect on this, you're like, wait a minute, you mean just like the baseball? Yes, just like the baseball. But the x component, doesn't the car start off with an x velocity driving off this cliff? And it continues to have an x velocity as it drives off this cliff. And it continues to have an x velocity driving off this cliff. And it continues to have an x velocity driving off this cliff. The fact that there's no acceleration in the horizontal direction, the fact that gravity only operates in the vertical, means that that velocity vector in the horizontal should be the same the whole time, yeah? In other words, if I start up at the top for the car, I'll even label it car. For the car, V1y, if I drive off of a cliff horizontally, is still 0 meters per second, just like it was for the ball. V1x, though, remember, stunt driver, car, let's just say it's 10 meters per second in the x direction. When it hits the ground, the velocity for the car in the x direction is still 10.0 meters per second, neglecting drag. But this is kind of an interesting thing. It picks up velocity in the vertical direction the same as the ball did. Again, neglecting drag. Okay? And there are going to be some people that say, wait a minute, doesn't a car kind of act like its own little parachute, slowing itself down as it falls? Picture what I'm talking about there? It's got a cross-sectional area. It's going to impact air particles. But again, we're assuming zero drag. And we're going to assume zero drag unless you're told otherwise, okay? But as this thing falls, assuming zero drag, V2y would be 40.0 meters per second. And in our course, we're going to assume zero drag unless you're told otherwise. People ask questions like, find the impact velocity of the car. Well, the launch velocity of the car was 10 meters per second to the right. But the impact velocity of the car has got to be the sum of those two vectors, right? So the impact velocity, I'd say, okay, well, at the moment when it smacks into the ground, I'm going to have a v2x, I'll have a v2y, and the resultant, the velocity that it hits the ground at, would be the sum of those two. That's v2. Not only would you be able to calculate the magnitude, because hey, look, v2x is 10 meters per second, v2y is 40 meters per second, but you could figure out the direction. because this is a vector after all. We should really know the direction of this V2 value. So we say, all right, well, the magnitude, that's a Pythagorean theorem problem. I say V2 is equal to V2x squared plus V2y squared, all rooted. I sub in my values. I got V2x, 10 meters per second squared, plus 40 meters per second squared, square rooted. And we're becoming pros at Pythagorean theorem over here. So I'll just say it ends up being 41.23 meters per second. And the small inner child that I have that wants to be satisfied with it being 1, 2, 3, 4 or something like that, I'm like, oh, it's 4, 1, 2, 3. But that's still a good answer, okay? Like I'm not fully satisfied, but I feel good. And then in terms of sig figs, I look at the values that I was using here. It was 10.0 and 40.0. So really I should say it's approximately 41.2 meters per second. And then for the direction, because direction's a part of velocity, I could say, okay, well, I'm going to use the tan ratio because I feel very confident about this opposite and this adjacent. And I'd say, okay, well, the tan ratio is V2y over V2x on impact. So theta is going to be tan inverse. V2y was 40 meters per second divided by 10 meters per second. Theta equals, I get 75.96 degrees, rounded off to 3 sig figs, give me, oh, that's kind of ugly, but 76.0 degrees. And then there's always people like, well, okay, so how am I going to express this? There's no north, south, east, west. All you've told us so far is how to deal with north, south, east, west. Well, if I think about this this car is coming down at an angle. You notice that it's at an angle below the horizontal? If I was launching a car off of a ramp, it would be launched at an angle above the horizontal. This is a car that's coming down at an angle below the horizontal. Look at the diagram, right? So I've calculated that theta, and not only that, when I drive cars off of cliffs, I fully expect them to hit the ground at a steep angle. And so I'm okay with this 76 degrees because it's a steep angle. So it's below the horizontal, and it's a steep angle, and I feel okay about that. Not that I've driven cars off of cliffs, but like I have the sense of this thing, right? And so I say, all right, well, the car's impact velocity is 41.2 meters per second. And the way that I'd express this, because it's a side view, it's not a north, south, east, west overhead view, the way that I'd express it is 76.0 degrees below horizontal. Like I said, if I was launching a car off of a ramp, I might have said above horizontal. But this is below the horizontal. It's coming in at an angle downward. 76.0 degrees below horizontal. And I want to make this little note. I'll make a note in red because it's important. All angles for projectiles are communicated relative to horizontal. All of them. That's the way we're going to operate. And people say, well, why would you have a rule like that? Well, the fact is we live on a planet that's primarily covered in water. Water lies flat. The horizon lies flat. We don't have anything in the surrounding nature that always stands up straight. Even trees lean over. My goodness. And you can't count on a building to stand forever. It makes sense that we're going to make all of our angle measurements for projectiles relative to the horizon. It's just logical. It's not because of some arbitrary rule. It's like because we live on a water world, okay? So everybody kind of just rolls with that. Now here I got this person that's going to run off of a cliff. This person's a little bit more daredevil. They're going to they've stripped away the car. They're like, adventurous type. Still got to give ourselves a reference frame. So we're going to give ourselves an up, down, right, left. And I still think I'm going to stick with a positive downward and a positive to the right, negative to the left. Now this person's going to run off a cliff. And if you've ever done cliff diving, some people have like at a cottage or something like that, then it's a thrill. If you've never done it, someday make it a part of your plans. How many people have done cliff diving before? It's always a minority of people, right? But just try it out. Recently I was at Canada's Wonderland. I watched the cliff divers, or it's just a fancy diving board, really. But they jump off. They do some really great acrobatics, whatever. If you ever go to a resort, sometimes you have it's a bit of a performance. People do like a cliff diving performance or whatever. It's actually kind of hard to truly run horizontally off of a cliff. The reason is because we all want to not die. Really, if you ever try running off a cliff, think about it. You're going to get to the edge, and you're going to do a little playful skip at the end, right? You ever run at a cliff, and there's this last second common sense oh my gosh, I'm going to die, it's a cliff, and then your will to have adventure forces you over the edge or whatever, right? Anyway, if you really wanted to have somebody run over the cliff, truly run over the cliff, either they have to be a very practiced cliff diver, or you have to blindfold somebody and tell them they're in a field and say, hey, run over there, and they'll just run over. Anyway, don't do that. But that's so dark. Okay, but running off of a cliff is actually a hard thing to do without giving a little skip at the end, right? So this person, though, clearly practiced. They're going to go off the cliff. Okay? They're going to follow, as we say, a nice parabolic path. Now, as they follow the path, I want to add in some information. I'd like to say that this cliff, the cliff in question here, this is a 100-meter tall cliff. So that means that as they fall, they're going to have a displacement. This is a delta D. They're going to have a displacement in the y direction. So a nice clear y equal to 100.0 meters. They're going to go down 100 meters. Now, interesting thing about this cliff, from the point that they launch off the cliff, see this point here is directly below where they launch off the cliff? From that point onward, I didn't tell you this until just now because I didn't want to worry you. There's a shark.
What?
You can tell there's a shark because there's a fin.
That's a dolphin.
Okay? Not a dolphin. Trust me. Been there. All right. So what I want to say is that the displacement to the shark is 110 meters. Okay? And what I'd really like to know here, and I don't have enough information to tell yet, what I'd really like to know is if I land right on the shark at 110 meters, becoming shark food, or if I can successfully jump the shark. Not a lot of people can successfully jump the shark. All right, so let's see how this works out. Got to know a little bit more information about this person. Turns out that this person is fast. Since they're running horizontally, we're going to say that V1x is equal to 0 meters per second. Sorry, V1y. V1y, that's important. V1y is 0 meters per second. But they are fast. Because V1x is 30.0 meters per second. Think about what that means.
What?
From now to now, 1,000, 30 meters. This is definitely like an employee of Marvel or DC. Okay, so this is a fast person. See if Marvel can jump the shark. Okay, 30 meters per second. So what we would like to do first, because it says here that we want to find the flight time. Before we do that, I'd like to take stock of what we know, okay? Stuff that I know. In the y information, I know that the person's V1y is equal to 0 meters per second. Their V2y, when they splash into the water, here, I have no idea. Not something I know. Their acceleration in the y direction, well, that's actually 9.81 meters per second squared, and so I guess I could have written that as AG. Happens to be down, down happens to be positive. And the displacement in the y direction is 100 meters from the top of the cliff to the bottom of the cliff. See up here, all the way to down here, 100 meters. And we declared down to be positive, so that's actually a positive 100. Just like the 9.81 is positive because it's downward. We'll mathify this stuff. And the delta t Well, as I write this out, V1, V2, acceleration, delta D, delta T, that's kind of my inventory, right? I haven't written out V average because that would be like composed of V1, V2, and delta T. I haven't written out delta V because that would be composed of V1 and V2. This is like my bare bones inventory. That's my inventory. That's all my Y information. But I don't know the flight time and I don't know the splashdown velocity. Okay? My X information as I take my inventory. My X inventory is, well, V1X, apparently 30.0 meters per second. V2X, well, I guess if you want to press it, it's still 30 meters per second because, as we said earlier, there's no drag, no acceleration in the horizontal. Going to stay same. So I can even make the statement, acceleration in the X direction is 0 meters per second squared. And this is always going to be the case, that it will always be 0 in the X direction. Okay, so that's default for projectiles, okay? Delta D in the X direction, I don't know. Just a reminder, delta D in the X direction is how far in this direction the jumper jumps, okay? Not the shark, so I can't just sub in the 110. There's going to be people that are tempted to put in the 110 because you're like, oh, I see an X thing, I'll put it in there. No. I want to know if I jump the shark. So I'm going to figure that delta dx out perhaps later because that's a part of a later question. And so I want to go back up here. The question now is find the flight time. Now, what controls how long it's in the air for? Isn't it how far you fall? And so people say, hey, am I going to be an X thinker or a Y thinker? And in this case, I'm going to be a Y thinker if I want to know how long I'm in the air for. Because how long I'm in the air for is limited by how long it takes for me to smack into the ground. Or into the water, I should say. Not into the ground. We got water down below. We're keeping everything safe. And so I think to myself, well, if I know this inventory, I know V1, I know acceleration, I know delta D, I actually have this nice equation that I could use. I go shopping through my equations of motion to see which of these variables are going to, check the box. And if I do that, I check my inventory against my equations, and I say delta dy is equal to v1y. Notice I'm writing in y's now, not just delta d equals v1t plus 1/2 at squared. I'm adding in the y's because I want to specify that if I'm thinking about y information, I can only use y information together in a single equation of motion. I can't mix and match and use x information in that equation as well as y information. In other words, if I use this equation, I can only draw information from this column in my inventory. I can't also draw information from this column. You're not allowed to match, okay? And so people talk about this as x and y motion independence. We have to keep them independent. We have to keep them separate because the acceleration only operates in the vertical. So I got to keep it with the velocities in the vertical and the displacement in the vertical. But as I look at this, I go through my inventory and I think, well, what do I actually know? I know the displacement. I know v1y. I know acceleration. And there's going to be people among us that are like, oh no, I have to use a quadratic here. But in this case, this is a special case, I don't. Can somebody tell me why I don't have to use a quadratic in this case? Yeah?
V1y is 0, so the first one cancels out.
Yeah, since v1 is 0, look at this, v1y is 0, I get to say, that means that whole term becomes 0. And so that's a convenient thing. And different people that have been doing their homework with equations of motion know that we can adopt these kinds of little strategies sometimes. And so this time, that's a strategy I'm going to make use of. But that simplifies the expression out to delta dy equals 1/2 ay. Oh, I didn't square it. You're right. Thanks for calling me out on that one. 1/2 ay delta t squared. And if I want to get this time now, actually that's not so bad. I'm going to multiply both sides by 2. So I get 2 times delta dy equals ay delta t squared. Notice I took that 1/2, multiplied both sides by 2. Then I'm going to divide both sides by ay. And so I get 2 times delta dy over ay equals, and I could say equals delta t squared, but can you guys give me permission? Can I just square root both sides? It'll save us a line of math, okay? All right, cool. So I got my delta t. I'll pop up here to the other side because I've run out of space in that column. and I say delta t is equal to, I'll sub in my values, 2 times 100 meters. Remember, I'm saying it's positive 100 meters because we declared the downward displacement to be positive. Also, acceleration due to gravity is positive because it acts downward, and we said down was positive, so 9.81 meters per second squared, and then square root it. But can I make a point here? If I had decided, if my mood had struck me differently today, and if I had said that down was negative, wouldn't the 100 have become negative? And wouldn't gravity also be negative? And wouldn't the negatives have canceled each other out? And so the reason I bring that up is not to be confusing, but to say, hey, as long as I'm consistent, it's all going to work out, okay? But I got to be consistent. Okay, so I've called down positive this time, and I did that strategically because I like to have as few negative signs as possible, because if you're like me, a lot of my silly mistakes are negative sign mistakes. And I know a lot of people have that problem, okay? Anyway, I do my math, and I believe in you. I know you can put this into your calculator. I get 4.5152 seconds as my fall time. Of course, I round that off to 3 sig figs, 4.52 seconds. And I could have it therefore, the jumper, jumper takes 4.52 seconds to fall. Now here I am talking about fall time. The question used the word flight time. You need to be able to roll with the synonymous terms, okay? So sometimes people will use fall time, sometimes they use flight time, sometimes, especially in sports, you'll even see the phrase hang time. Anybody ever heard that in basketball? People talk about their hang time? Okay, so hang time could be another phrase that we talk about for how long somebody's in the air for, or how long a ball is in the air for, or whatever, okay? So we've got to be able to roll with those slang terms. But if there is a slang term that pops up, never be shy about asking. Like if you saw hang time and you're like, what does that mean? I'm going to tell you, okay? All right, so find the range. This is actually another slang term. Range is something that shows up oftentimes with archery, with rifle ranges, for example. And what I want to draw attention to is that when people talk about range with projectiles, it's a common enough word that I'm going to continue to use it. Range with projectiles means the horizontal distance that something travels before it hits the ground. I put that in brackets down below. That's what range is. So we'll talk about range, but another thing to point out is that the word range in math class, in the context of domain and range, means something different. Unfortunately, in math class, doesn't domain mean the horizontal stuff, and range means the vertical stuff? Language is terrible, right? I mean, we need it to communicate, but sometimes it's annoying when it means opposites in different contexts. I'm telling you, range in physics, in projectiles, means how far it goes, okay? I know that that's different in math class. Okay, so I'm not that worried about it. I'll just make a little note. We're looking for delta dx, okay? That's the displacement in the x direction before it smacks into the ground. And as I do my inventory, I look through my equations of motion, and I match it against what do I know. And something that came up, I'm not even sure if this is the best decision, but as I looked at my equations of motion, this came up in my mind. I thought v1x plus v2x divided by 2. Look, I know those guys. That's v average x. Now there's going to be some other people that'll say, oh, they were both 30. Well, if they're both 30, isn't that already a statement that v average x is 30 meters per second? And so if you have that mindset on things, yeah, you're absolutely correct. The best thing about this is we can both be correct. Cool? So as I was thinking about this, I thought, oh, v1x plus v2x, well, that's just 30 meters per second plus 30 meters per second. Notice I'm just drawing from my inventory. Divided by 2. Got to remember to divide by 2. And then multiply by, hey, I'm gonna believe in myself. I think I got that one right. And I'm going to use the unrounded value, 4.5152. Always the unrounded value, never including premature errors with the rounded value. And I do my math. Can somebody with a calculator help me out? Because I feel like I'm not trusting myself now. What do we get? How far is this person going to go before they hit the ground? Yep. 0.456, you say? Okay. All right. And I could round it off. I think we had 3 sig figs, so let's round it off to 3 sig figs. 135 meters. And I might ask, and I could even say to the right. I might ask the question, did we jump the shark? Victory? Jump the shark. Okay, so therefore, the jumper jumped the shark. Now, and had a range of 135 meters to the right. What I know about sharks is that I'm now only 25 meters away from a shark. So I really hope this person can swim as fast as they can run, right? So they're not out of danger yet, but if they really are working for the Marvel people, I'm sure they're going to be fine, okay? I gotta pause. Does anybody have a question about that? Feel good? All right. I mean, like everything, we're gonna need to follow this up with practice. You know that, right?